today's is the 9th lecture of this course and 7th lecture on equilibrium carrier concentration. Let us see what we have achieved in our discussion on the intrinsic carrier concentration, which we completed in the last class. So we have shown that this is the allowed levels and density of states picture. The density of states function is close to parabolic near the band edge. Then the fraction of the occupied states function, that is the Fermi-Dirac function, is as shown in this diagram. From fraction of occupied states and the density of states function, you get the excess carrier concentration, which is the area under the product of NE and FE functions, which is this. So this is your Ni, intrinsic concentration. Similarly, one can calculate the intrinsic hole concentration, which is equal to Ni. Now this is the actual picture. Now what our formula that we have derived shows is that you can replace the actual picture by a simpler effective picture, which is given here. So in the effective picture, you have Nc per centimeter cube density of states at the conduction band edge, Nv per centimeter cube states allowed for electrons at the valence band edge, and then you can multiply this allowed states by the fraction of occupied states function, which is the Boltzmann approximation of the Fermi-Dirac function, and then you get the simple formula Ni is equal to Nc, the allowed states, multiplied by the fraction of these allowed states which are occupied under the Boltzmann approximation, exponential minus Ec minus Ef by Kt. Ni is the number of occupied states in the conduction band. Similarly, one can write an expression for Pi, for the unoccupied states in the valence band, and finally you know that Ni is equal to Pi. Now from these three relations you can eliminate the Fermi level and you get the intrinsic concentration as square root Nc Nv into exponential of minus energy gap divided by 2 times Kt, and then you also get the Fermi level, which for intrinsic semiconductors is called the intrinsic level E suffix I. This is Ec plus Ev by 2 minus Kt ln square root Nc by Nv. This term is generally very small, so one approximates Ei by Ec plus Ev by 2, and this is what is shown here. The Ei is almost in the middle of the energy gap. So the Ni, if you plot on a log scale as a function of reciprocal of temperature, the slope of this line will almost be a straight line, and its slope will be minus energy gap by 2k, and that is how you can find out the energy gap of semiconductors from measured concentration versus temperature behavior. It is important to note that this Nc, the effective density of states, is not exactly the same as the total number of states in the conduction band, or for that matter Nv is not the same as total number of states in the valence band. For example, these total number of allowed states in the valence band we have seen is 4 into 5 into 10 power 22, whereas Nv is of the order of 10 power 19. So one must not confuse Nv as simply the area under this curve. This is an effective picture. Now in today's lecture we will be discussing a model for the extrinsic semiconductor. Under equilibrium we will be discussing a model for the carrier concentration. So if you recall, what we want to explain here is the behavior shown in this slide. So we would like to explain how you get a flat portion of constant majority carrier concentration over a certain temperature range, and adjacent to this you have for low temperatures an exponential behavior of the concentration with temperature, and also for very high temperatures an exponential behavior of the concentration. Another thing that we want to explain is the fact that minority carrier concentration is given by intrinsic concentration square divided by the majority carrier concentration. So in an n-type semiconductor, for example, hole concentration is equal to Ni square by Nn0, that is the electron concentration, or in general in any doped semiconductor P0 into N0 is equal to Ni square. So this fact also we would like to explain. Now the way we will proceed for deriving this information will be the same as that we have used for deriving the intrinsic carrier concentration. That is, we will first consider a bond model, a simple qualitative model of the semiconductor, and then we will consider the energy band model of the doped semiconductor. So, extrinsic semiconductor bond model. At the outset, let me state that we are considering a uniformly doped semiconductor. So, uniform doping, and we will assume that there are no defects or impurities, no defects but only impurities. Okay. It is very important to understand the meaning of the term uniform in uniform doping. It is very difficult to place the impurity atoms in a semiconductor at regular intervals. Just as you have the silicon atoms in a silicon crystal at regular intervals, it is not possible to have impurity atoms placed at regular intervals that easily. This is because the processes that are used to introduce impurities normally result in random location of the impurity atoms. So, that being the case, now what is meaning of uniform doping? So, the atoms are not regularly, impurity atoms are not regularly placed, they are randomly located. The meaning of uniform doping is as follows. Supposing I have 10 power 16 per centimeter cube of impurity atoms, then I will find that if I take the semiconductor and I look at the different 1 centimeter cube blocks of this semiconductor at different places. So, each of this is a volume of 1 centimeter cube. I am showing the picture in 2 dimension. Then I will find that the concentration in any of these 1 centimeter cube blocks will lie between 10 power 16 plus or minus square root of 10 power 16 per centimeter cube. So, there is a deviation because the atoms are randomly located. Definitely the concentration of impurity atoms cannot be exactly 10 power 16 everywhere. So, there is a deviation, but the deviation lies within plus or minus 10 power 16 square root of that. Now, why it should be square root, that we will not discuss, you take it as a fact, but it is important to note the result is that square root of 10 power 16 is 10 power 8. So, 10 power 8 is much less than 10 power 16. So, this is the meaning of uniform doping, that the average value is very, very large compared to the deviation, okay, and that is why we can assume the doping to be uniform, though the atoms, the impurity atoms are located in a random fashion. So, in general, if n is the doping, then the atomic concentration will lie within plus or minus root n of n. Okay. The next assumption that we will make in deriving our models is that the concentration of impurity atoms, 10 power 16 per centimeter cube is an example here, the concentration of impurity atoms will be much less than the concentration of silicon atoms. So, that is to say, this is called a dilution approximation. So, what it means is that the concentration of impurity atoms n is much less than the concentration of silicon atom. So, silicon atom concentration. So, silicon atom concentration, for example, is 5 into 10 power 22. per centimeter cube, and N is the concentration of impurity atoms. So this impurity concentration is much less than 5 into 10 power 22. So you have impurity doping in the range of say 10 power 13 to 10 power 20. That is the kind of range we are talking about for N. Okay, N lies in the range 10 power 15 to 10 power 20. In fact, this 10 power 20 is at the higher range. Sorry, this is not 10 power 15, this is 10 power 13. 10 power 20 is a higher range. We will be considering models for moderately doped semiconductors around 10 power 16 and so on, and we will assume that the models can be used over a wider range, though we will see there will be some deviation as you go towards the higher doping levels. So what is the consequence of this dilution approximation? The word dilution means that the silicon is like a dilute solution. It is not a liquid, but it is solid. So it is a solid solution which is dilute. That means the impurity is being regarded as a solute, and the silicon atoms are regarded as the solvent. Okay, and the solute concentration is very, very small. What are the consequences of this particular assumption? So the first dilution approximation implies, firstly, there is no interaction among the impurity atoms. So for example, 10 power 16 if you take as a doping, 10 power 16 impurity atoms in 5 into 10 power 22 silicon atoms, which means 10 power 6 one impurity atom for every 5 into 10 power 6 atoms of silicon. Okay. So one impurity atom is surrounded by 5 into 10 power 6 atoms of silicon. This evidently means that the next impurity atom will be so far away from this particular impurity atom that there cannot be any interaction between them. This simplifies the picture because we can take every impurity atom to be isolated and then discuss what is happening when you place such an impurity atom in silicon. So the second consequence of dilution approximation is that the silicon crystal structure is unaffected. So this means the interatomic distance between silicon atoms is the same as that in a pure semiconductor. So whenever I talk of silicon, it must be understood that you can extend it to any semiconductor unless I make statement otherwise. Now under such conditions, we will try to derive the model. So let us see what is the bond model for the case of silicon doped with, let us say, phosphorus impurity. So phosphorus doped silicon. Now phosphorus is a group 5 element. So whatever we discuss now is applicable to group 5 impurities in general. If you introduce phosphorus impurities in silicon, what is the picture? So let us draw the bond model of pure silicon first, that is a matrix, a two-dimensional matrix. And we assume that in this matrix somewhere instead of silicon you have introduced a phosphorus atom. Now one can ask, why should the phosphorus atom be located exactly in the place of silicon? Well, it is not necessary. The phosphorus atom can also be between two silicon atoms, but we will not consider such complications. We will take a simple situation. Further, we are taking only one phosphorus atom because, as we have said, under dilution approximation, the other phosphorus atom does not have any interaction with this. Now let us see what is the consequence of this. Let us talk about T equal to 0K first. The phosphorus has 4 electrons in the outermost orbit. They will participate in bonding with the 4 neighboring silicon atoms. Now there is a 5th electron. What happens to the 5th electron? A simple model says that the 5th electron will simply revolve around this phosphorus atom, just as you have the picture of a hydrogen atom where there is a positively charged nucleus and an electron orbiting around it. Notice that since phosphorus is a group 5 impurity, it has 5 electrons in the outermost orbit. So without this particular electron, the phosphorus atom is positively charged. Now it is important to note that the orbit radius is rather large and it is not as small as you have in a hydrogen atom. Now this is because the medium here is silicon and not vacuum. So one must consider the effect of the dielectric constant of the medium in which this particular electron is orbiting. So we are saying that this radius r is much more than that you have in a hydrogen atom. Let us see why. The force between this positively charged phosphorus and the negatively charged electron, this force F, we know is proportional to 1 by epsilon r, because if you write an equality sign here, then the force is given by minus q square by 4 pi epsilon naught epsilon r square. So what is of interest to us is this epsilon r. So we find that the force is proportional to 1 by epsilon r. In other words, if you have a dielectric medium whose epsilon r is more than 1, then the force between the two charges will be less than that in vacuum. Now epsilon r for silicon, epsilon r for silicon is about 12. So which means the force between two charges, assuming some distance r between them, will be 12 times smaller in silicon than in vacuum. Now it is the reduced force that is responsible for a larger orbit. If you calculate the energy of the electron in the orbit using the Bohr model of the hydrogen atom similar to that, you will find the energy is proportional to 1 by epsilon r square. So this means that the energy of this electron orbiting around the phosphorus atom in silicon would be 144 times less, because epsilon r square for silicon would be 12 square, 144 times less than that of a hydrogen atom. Now this energy of the electron that we are talking about is actually the energy required to free the electron from this particular orbit and take it to infinity. So this is the ionization energy of the electron or phosphorus. So we can call this as E ion. So the energy required to free this electron, which is E ion, is proportional to 1 by epsilon r square. So what this means is, because of the presence of silicon atoms surrounding phosphorus, this phosphorus atom can be ionized rather easily. when it is placed in a silicon medium. The same phosphorus atom, if you move out of silicon, its ionization energy will be much larger. It turns out that ionization energy of phosphorus is about 0.045 electron volt. Compare this with the ionization energy of the silicon atom. A silicon-silicon bond, to break this, the energy required is 1.1 electron volt. So this is very small compared to that. Now as a result, what will happen is that this electron, which is orbiting around the phosphorus atom at T equal to 0 K, can be freed very easily when you raise the temperature beyond 0 K. So now let us see for T greater than 0 K what is happening. For T greater than 0 K, this electron becomes free of this phosphorus atom because of thermal vibrations of silicon atoms. Now, a large number of electrons associated with phosphorus atoms, phosphorus impurities which have been introduced, will become free at much lower temperatures than that of silicon, than the temperature at which the large number of silicon atoms will break their bonds. That is why even for small temperatures, most of the impurity atoms, most of the phosphorus atoms would get ionized, and each phosphorus atom would contribute to an electron. Now please note that when an electron becomes free of a phosphorus atom, it becomes available for conduction, but no hole is created. This is because a phosphorus atom without an electron is not a vacancy, via which the bounded electrons of the other silicon atoms can participate in conduction. So ionization of the impurity results only in one type of carrier, namely the electrons. But as you raise the temperature, it is also likely that some silicon to silicon bond will break and it will give rise to a free electron. Now this process, which is electron hole pair generation, because a broken silicon bond, we have said already, is a vacancy or a hole via which the bonded electrons participate in conduction. So this process of electron hole pair creation is an independent process which also goes on. So like impurity ionization, which gives rise to an electron, there is also silicon ionization which gives rise to an electron hole pair. So this will be an additional source of carriers. So if you want to now summarize the processes which give rise to free carriers in a doped semiconductor, that would be something like this. So sources of carriers in extrinsic semiconductors. The process of impurity ionization gives rise to an electron. We will see how it can give rise to a hole also if you dope the semiconductor with boron. So impurity ionization in this particular case where phosphorus has been introduced into silicon gives rise to only electron, and the energy required for this is 0.045 electron volts. You have another parallel process, namely silicon ionization, which is also called thermal generation. So the word generation in the context of semiconductors is used for creation of an electron hole pair because of thermal vibrations. So this results in an electron hole pair, so both types of carriers, electrons and holes, and the energy required is 1.1 electron volts. Since this energy required is much higher than 0.045, so therefore at any temperature, generally unless the temperature is high, the impurity ionization process will dominate over the silicon ionization process or thermal generation process. So supposing Nd is the concentration of phosphorus atoms, where N stands for the concentration and suffix D stands for the word donor. A phosphorus atom is called donor because it donates an electron. So Nd is the concentration of the phosphorus atoms introduced. Then we can use a suffix plus a superscript plus to show the concentration of ionized impurities. As we said, at T equal to 0, if you take, no impurity will be ionized, the electron will be orbiting around the phosphorus atom, it is not free for conduction. So there are no electrons or holes even in a doped semiconductor at T equal to 0 K. Now as you raise the temperature, the electrons start becoming free of the phosphorus atoms, so impurities start getting ionized. So Nd plus represents the impurities which are ionized. So Nd plus by Nd will generally be less than or at most equal to 1. Now what we are saying is that at any temperature which is not very high, for example supposing you take room temperature, so room temperature you will find that most of the impurities are ionized, because the energy required for this is only 0.045 electron volts, and average energy of a particle under equilibrium conditions, whether you take electrons, holes, photon or phonons, we have said is K times T, that is 0.026 electron volts. So if that energy is 0.026 electron volts, to free an electron from a phosphorus atom, an energy of 0.045 electron volts can be given by even 2 particles, whereas to break a silicon-silicon bond and create electron hole pair, you need to give 1.1 electron volts or 42 particles have to converge. We have seen this. So therefore at room temperature you will find all the impurities will be almost ionized, so Nd plus by Nd will be almost equal to 1, whereas the number of silicon atoms which are ionized will be very, very small, comparatively small. Now based on this particular model, we can easily explain a portion of the concentration versus temperature diagram. So supposing I am talking of N naught, that is electron concentration in an N-type semiconductor, so I will write it as N naught, because electrons will be, it is clear that in a phosphorus doped crystal the electrons will be in a majority. You have electrons being created by impurity ionization as well as by silicon ionization of thermal generation, whereas holes are created only by thermal generation. So electrons are in a majority, so majority carrier concentration N naught versus 1 by T, we have said is something like this. If the same thing you plot as a function of temperature on a linear axis, then what this same curve means is that you are going to start from 0 and the curve is going to saturate, that is this portion. So this portion is coming here, this portion is coming here, and this portion will go here in this right extreme on a linear temperature scale. Now we can explain the behavior up to this point from 0. So at T equal to 0, no electrons or no holes, so concentration is 0. As your temperature rises, the concentration increases. Why? Because the process of impurity ionization is there and thermal generation is there. But as we said, the impurity ionization process will always dominate over thermal generation because of the small energy. So by a temperature maybe around 50 K or 100 K, 50 to 100 K, the exact temperature depends on the value here. So for different impurities you have different ionization energies. By this time all the impurities are ionized, or Nd plus by Nd becomes almost equal to 1. So once that happens, your concentration has become almost constant, because although this particular process of silicon ionization or thermal generation is going on increasing with temperature, the concentration because of this concentration is very, very small compared to that concentration. So that part one can show something like this. So this dotted line shows the contribution because of thermal generation. Or silicon ionization. Now this shows the contribution because of impurity ionization. So I will show it with a different color. So this is impurity ionization. I will remove this curve to avoid any confusion. So impurity ionization, already all impurities are getting ionized by this temperature, which is less than room temperature. So you are reaching a saturation. So though this component is going on increasing, this thermal generation component is very, very small compared to impurity ionization because of the different energies associated with these two. And then it is only beyond this temperature here that the thermal generation is becoming comparable to the impurity ionization. Okay? And so here beyond this, though the impurity ionization has saturated, thermal generation is increasing and it is going beyond this, so the carrier concentration now starts exceeding. That is how you can explain how you get an increasing portion in the beginning, then a flat portion of the concentration, and then again an increasing portion. So this kind of a behavior arises from the two particular sources of carriers, namely the impurity ionization and thermal generation, and their individual behaviors. Now this is the kind of bond model we have for a phosphorus doped silicon. We can have a similar model for boron doped silicon. So let us take boron doped silicon. Boron is group 3 impurity. We will show shortly, as I will say later, the ionization energy of boron is also about 0.045 electron volts. Okay? Let us see how this picture would be different in the case of boron. So here the phosphorus is being replaced by boron. Now let us redraw this part of the picture to understand how I can say that at t equal to 0 k, at t equal to 0 k, you can have a hole revolving around a negatively charged boron atom. Let us see how this is true. So let us say this is the boron atom here. Boron has 3 electrons in the outermost orbit, therefore you will have 3 bonds. However, one bond will be broken because boron does not have a 4th electron, whereas silicon has a 4th electron here. Now this particular picture of a boron atom without an electron or a broken bond can be regarded as equivalent to this picture of a boron atom negatively charged with a hole revolving around it. How can that happen? Well, if you take for t greater than 0 k, it is possible for an electron from any one of these bonding processes, okay, silicon to silicon bonds, electrons located in any of these silicon to silicon bonds to jump into this site and fill in this place and establish this bond. If that happens, the electron which is coming to this boron atom will make this boron negatively charged, but since the electron has come from somewhere nearby, let us say it has come from here, it will leave behind a vacancy here. Now note that such a thing can happen only at t greater than 0 k. So for t greater than 0 k, the absence of an electron near the boron site results in a broken silicon bond somewhere else, because the boron atom likes to accept an electron at this site to fill in this bond. and it results in a hole. So T greater than 0K, each boron atom which is ionized will contribute to a hole, to breaking of a bond. That is why boron atom is called the acceptor atom. So we could regard therefore the picture for T equal to 0K to be a broken bond of silicon but which cannot take part in conduction, because at T equal to 0K you have no electrons or holes, no conduction in a semiconductor. So this fact can be represented as a hole which is bonded to the boron atom which is revolving around it. Once the hole is bonded, that means it is not a hole at all in strict sense, because hole is a mobile carrier, something that can move in response to the electric field. So this is a kind of imagination that we do to get a simple model. So the only difference between phosphorus and boron, if you adopt this model, is that at T equal to 0K, a phosphorus atom is equivalent to a positively charged nucleus with an electron revolving around it, whereas a boron atom is equivalent to a negatively charged nucleus because it has taken the 4th electron from somewhere else, and a hole or a positive charge revolving around it. Now that being the case, the energy associated with this revolving charge, it is very clear, would be the same as the electron energy associated with the electron which was revolving around phosphorus, because all that has happened is sign of this has changed, sign of this has changed. Okay, so that really doesn't change the numerical value of the energy. So again you have, by the similar arguments that we have used for the phosphorus atom, because of the presence of silicon medium, the ionization energy of boron reduces drastically, energy proportional to 1 by epsilon r square, and that energy turns out to be 0.045 electron volts. Now please note that this method of calculating energy, ionization energy of impurities, okay, is qualitatively correct, but for different impurities it is not necessary that the value you calculate by this approach will match. This is because the picture is somewhat more complicated than the simple Bohr model that we are assuming, but that doesn't matter, we can still continue to use this model for a qualitative understanding. Now we can proceed as we have done for the phosphorus atom, and for T greater than 0K, this charge carrier becomes free, so it results in a positive charge, hole. And similarly you also have a parallel process of silicon ionization which results in a hole and an electron pair. So in the case of boron, you are getting holes by two mechanisms, one is impurity ionization, another is the thermal generation or silicon ionization. Therefore the holes are in a majority, and that is why this semiconductor will be called p-type. So again, if you see the sources of carriers in semiconductors, look at this slide. You have two processes, impurity ionization in the case of boron resulting in only hole, it does not give rise to an electron, free electron. Energy is 0.045 electron volts. You have silicon ionization which results in electron hole pair generation, energy 1.1 electron volts. So the result will be similar to what we have drawn here for the phosphorus, the only difference being this N0 will be replaced by P0. That is the majority concentration of holes in a p-type semiconductor under equilibrium. Okay, so here you will have impurity ionization, boron's atoms getting ionized, and ultimately almost fully ionized by about 50 to within a range of 50 to 100 K, which is much lower than room temperature, and then saturation. So impurity ionization is saturated here, Na minus by Na. Na is the impurity concentration, A stands for acceptor, because boron accepts an electron, or a group 3 impurity accepts an electron, it is called an acceptor. And Na minus, a minus superscript indicates those fraction of Na which are ionized. So Na minus by Na is less than or equal to 1. After 50 to 100 K, Na minus by Na is almost 1, so it has saturated. You have thermal generation similarly taking place, which is much less for temperatures less than this value, and then thereafter the thermal generation takes over impurity ionization and you have this curve. So you have exactly a similar curve for boron impurity in silicon. Now we can write the relation between the majority carrier concentration and minority carrier concentration, or electrons and holes, in a following form. So if you take an n-type semiconductor, example is phosphorus or a group 5 impurity. Your equation is the electron concentration in an n-type semiconductor is equal to the ionized impurity concentration, that is the electrons contributed by ionized impurities, ionized phosphorus or donor atoms, plus the electrons contributed by thermal generation process. Now since the thermal generation process results in electron as well as holes, the electron concentration which results from thermal generation is same as the hole concentration in an n-type semiconductor. So therefore we can write capital P stands for holes in n-type semiconductor, suffix 0 under equilibrium. So Nn0 is equal to Nd plus Pn0. There is an advantage of writing the electron concentration contributed by thermal generation in terms of the hole concentration, because this equation is also called the charge balance equation. You can see when you write it in this form, electrons are negative charges, ionized phosphorus impurities or donor impurities are positive charges, and holes are also positive charges. So it is like negative charges equal to positive charges, statement of charge neutrality. That is why it is called charge balance. You can write a similar equation for p type. So p type, the impurity for example is boron or any other group 3 element. And here what happens? The holes are in a majority, so I will write hole concentration in a p-type semiconductor under equilibrium Pp0 is equal to the ionized acceptor impurity concentration, that is the carriers provided by impurity ionization plus the carriers provided by thermal generation. Now again thermal generation in this case results in electron hole pair, so the hole concentration provided by thermal generation is same as the electron concentration in a p-type semiconductor, because impurities do not result in electrons. Electrons can only be obtained from thermal generation in the case of p-type semiconductor. So I can write this as n suffix p0, electrons in p-type semiconductor under equilibrium. Now this is again a charge balance equation. Left hand side is positive charges, right hand side is negative charges. Okay. So there are several ways of interpreting this charge balance equation. So one is in terms of balance between positive and negative charges. Other way is in terms of the processes used for generating these charges. So left hand side is majority carrier concentration. On the right hand side, this represents impurity ionization. And this represents the minority carrier concentration or the thermal generation process. So you can, this can be called thermal generation or silicon ionization. So impurity ionization, silicon ionization, and alternately, or in addition to the fact that these carriers are created by thermal generation, you know that these are minority carriers. So left hand side you have majority carriers, these are the minority carriers. So we will also write here minority carrier concentration. So this is another way of interpreting the charge balance equation. The majority carrier concentration is provided by impurity ionization process and thermal generation process. On the other hand, this equation also shows, which is something very important, the minority carriers are provided only by thermal generation process, because only this process results in electron hole pair generation. So holes are minority in n-type semiconductor and electrons are minority carriers in p-type semiconductor. The fact that minority carriers are provided by thermal generation process is very important. We must remember this fact because, as we will find later, this particular fact is responsible for a slow response of minority carriers in switching conditions. Now with this we have come to the end of the bond model of extrinsic semiconductors. We can't derive any further information out of this model. As we have said, we have been able to explain this particular behavior of this majority carrier concentration. So in general we could write here majority carrier concentration. And this is the impurity ionization process, this is thermal generation process. So you can say this is the minority carrier concentration, thermal generation or minority carrier concentration. So we are able to qualitatively explain the shape of this carrier concentration versus temperature curve, majority carrier concentration versus temperature curve using the bond model. And we are able to explain why there is a significant flat range of this concentration. Okay? What we are not, however, able to derive from here is what is the concentration of minority carriers at any temperature. Okay? So we are not able to derive a value for this concentration. Nor are we able to derive the values of the majority carrier concentration. If you go to this graph, value of the majority carrier concentration under these conditions, that is low temperatures, that is the range of partial ionization, and at very high temperatures. Okay? In this range we can derive the expression for majority carrier concentration. That is very simple, because all impurities are ionized. Here the majority carrier concentration is same as the impurity concentration. So I will redraw this graph very clearly. This is the flat portion, this is temperature in a linear scale. Please note this is linear scale, and this is majority carrier concentration. Also on a linear scale in a semiconductor. This is 0. So I can show 0 of the majority carriers as well as 0 of the temperature, since the scales are linear. Here this flat portion, we know this value is impurity concentration. Now one can say, why is it that this flat portion is only impurity concentration? What about, though the impurities are fully ionized, there is a process of thermal generation also contributing to the majority carriers, but that process is very, very small. That is why something like this, you are not able to show on a linear scale the minority carrier concentration. Something like this. So this is minority carrier concentration. This is the region of partial impurity ionization. Partial impurity ionization. Now here beyond this all the impurities are ionized in this entire range, this complete impurity ionization. So we can find out the majority carrier concentration in the flat portion in this temperature range, which is called the extrinsic range. This is called the extrinsic range because in this region the semiconductor is extrinsic. Extrinsic means it is not intrinsic, that is one type of carriers are in a majority as compared to the other type. Strictly speaking, even in this region the semiconductor has an extrinsic nature because minority carrier concentrations are small, but the extrinsic nature is not fully developed. It is only here that the impurities which you have introduced to make the semiconductor extrinsic have fully ionized. So the extrinsic nature is fully developed only in the flat portion. In this region the extrinsic nature is getting lost because as you can see minority carrier concentration is becoming equal to the majority carrier concentration. So we will shift this here, this is majority carrier concentration. So majority carriers becoming equal to minority carriers, this is something like in a pure semiconductor electrons becoming equal to hole concentration. So extrinsic nature is getting lost. So this is not extrinsic range. So since the semiconductor becomes closer and closer to intrinsic semiconductor, this is called the intrinsic range. Semiconductor is entering intrinsic range, and this temperature at which beyond which the semiconductor starts becoming intrinsic is called intrinsic temperature, Ti. Okay, so this is the amount of information that we have been able to derive from the bond model. Impurity majority carrier concentration in the extrinsic range we can get very easily because it is equal to impurity concentration. However, we need to get this region behavior and that region behavior also to get a complete picture, and also we need to know whether what we have shown for phosphorus and boron, whether similar thing will be applicable for other impurities also, right. So to get a more complete picture we must go to the energy band model. Okay, so the energy band model will be the next topic of discussion. Now let us see if there are any questions.
Sir, you have explained the behavior of a semiconductor doped with only donor or only acceptor impurities. What happens when both type of impurities are present?
When both types of impurities are present, it is called a compensated semiconductor. Let us see what is the picture in such semiconductors. Now here we have a table giving the impurity and the charge balance equation. So if you have only donor type impurities, this is the charge balance equation. If you have only acceptor type impurities, then this is the charge balance equation. If you have both donor and acceptor type impurities, then the charge balance equation can be constructed in a similar fashion from the knowledge of these two charge balance equations. So we put all the negative charges on one side and the positive charges on other side, ionized acceptor concentration and electrons on one side, ionized donor concentration and holes on the other side. Now notice carefully that we have not used a suffix n or p either for n naught or for p naught. This is because we do not know the semiconductor is n or p type unless we know the relative magnitudes of Na minus and Nd plus. So if Na minus is more than Nd plus, then it will be p type, so as written here. Okay, so you have a p type semiconductor if Na minus is more than Nd plus. This is because your hole concentration will then be more than electron concentration. The same equation has been rewritten to show this. On the other hand, it will be n type if Nd plus is more than Na minus, because electron concentration in that case would be more than hole concentration. So N naught is equal to Nd plus minus Na minus plus P naught. So in this manner we can determine the concentrations and polarity of the semiconductor when both donor and acceptor type impurities are present. We will have further discussion on this compensated semiconductors in the context of the energy band model. With this, we have completed the discussion of the bond model of the extrinsic semiconductor. We will take up the band model in the next class.